All right. We're going to be looking today at lesson 7.2, so we're skipping 7.1. I'll talk a little bit later about what 7.1 is about and why I've decided to skip it. This dives right in and starts talking about the derivative of sine functions and cosine functions. So all of the rules that we have learned, the sum rule, the difference rule, the product rule, the quotient rule, the chain rule, I don't know if I have it up there, but the constant multiple rule, all of those rules are still applied when we're differentiating sine functions and cosine functions. And I'm just starting by telling you what the derivative of sine of x is with respect to x and what the derivative of cos of x is with respect to x. And it turns out that the derivative of the function y equals sine of x is dy dx equals cos of x, and the derivative of y equals cos of x is dy dx equals negative sine of x. And these will be given to you on a formula sheet, although they will appear in slightly different forms. What section 7.1 is a proof of some limits that you would need to prove these two statements. And perhaps at the beginning of tomorrow's class, or maybe even later today if we have time, I will show you how to prove, I think we just would have time to do one, how to prove that the derivative of sine of x is equal to cos of x. And it's found, that proof is found by applying the definition of the derivative, the limit as h approaches 0 of f of x plus h minus f of x over h, applying that to sine of x, and then taking a major detour because it's going to involve trigonometric limits, which is 7.1. I just feel that although you're going to see it next year in post-secondary, I think you'll be better off just diving in and differentiating. Okay? But again, I will show you the proof of the limit and the proof of the derivative later, if we have time. So, what is the derivative dy dx if y is equal to 2 sine x cos x? I didn't really spend a lot of time talking about this, but there's a pattern here. The derivative of sine is cosine. The derivative of cosine is negative sine. You need to know that to be able to do this. So the only thing you can do here so far is to think of 2 sine x cos x as a product of two functions of x. And then we're going to use the product rule. And that gives us dy dx is the derivative of the first. Now, I want to just stop and really dive deep into what just happened here. We have this rule going way back to, I don't know when, that says the derivative with respect to x of a constant multiplied by a function of x is the derivative, is the constant times the derivative with respect to x of the function of x. Okay? This is why when we first learned the power rule, we went from the derivative with respect to x of x to the n equals n x to the n minus 1, right? Yes? And then all of a sudden we went to the derivative with respect to x of a x to the n is a n x to the n minus 1. You see what I'm talking about here? You're moving the coefficient in front, multiplying by the, or the exponent in front, multiplying by the old coefficient. You understand the language here, right? Well, the reason we can do that is because of this rule here. We can take this a and put it in front, and then just multiply by the derivative of x to the n. And that's all that's happened when I've said the derivative of 2 sine of x is 2 cos of x. I'm saying the derivative of 2 times sine of x, according to the rule, is 2 times the derivative of sine of x, which gives you 2 cos x. That's the derivative of the first, times the second, which is cosine of x, plus the first, which is 2 sine x, multiplied by the derivative of the second, And the second is cosine of x, which has a derivative of negative cos, of negative sine of x. So we put this together, clean it up a little bit, and we get dy dx is equal to 2 cosine squared of x minus 2 sine squared of x. And if you're a little bit clever about it, you'll recognize that if you take a 2 out, and you should always consider factoring, I shouldn't say don't. There's no value in factoring that other thing as a difference of squares. That's not the point. But the point is that cos squared of x minus sine squared of x is cosine of 2x. Right? And that's always preferable to have a more compact thing. If you wanted to find critical values of x for the derivative, then rather than think of this equal to 0 or this equal to 0, you think of this equal to 0, and you do exactly what we did in the two questions that were asked about today. You let 2x equals a, and you proceed. That's maybe the first time that you see a real reason why an identity is useful in terms of solving an equation. So dy dx is this. The derivative of the function is this. Any questions with that first example? All right. Y is equal to cosine of x over 1 plus sine of x. Well, we're going to have to use the quotient rule, where we take the derivative of the numerator, and the numerator is cosine of x. And then the derivative of cos is negative sine. We multiply by the denominator. Then we subtract the numerator and multiply by the derivative of the denominator. And I hate to go back to the basics here and bore you with it, but I'm just going to write it here and then erase this. The derivative of 1 plus sine x, I know you know this. That's the denominator. The sum rule says it's the derivative of 1 plus the derivative of sine of x. We've been so caught up in applying derivatives that I want to make sure we understand the rules of differentiation, which is huge in this unit. The derivative of 1 is 0 because it's a constant. The derivative of sine of x is cos x. So that's why the derivative of the denominator is simply cosine x. And then we have to put over 1 plus sine x quantity squared. And there's nothing to be gained by taking 1 plus sine x times 1 plus sine x. If anything, we want to leave it in factored form in case we get a factor of 1 plus sine x in the numerator that can cancel. Speaking of which, we have some work to do in the numerator. There are two terms. Can we factor anything out? No. That means you're left with the task of multiplying stuff through. Even if you do factor something out, whatever you have left, you multiply it out. So negative sine x times 1 is negative sine x. Negative sine x times sine x is negative sine squared x. And then we have minus cos squared x. Well, it turns out that we have a 1 plus sine x on the top. Because if I factor that negative out, it should become clearer, I hope. If I factor that negative out, the sine x, which was negative, becomes positive. Both of these quadratic terms become positive. And hopefully you recognize that this is 1. I don't feel the need to rewrite that with sine x plus 1 on the top. This, well, I guess maybe I should. We have sine x plus 1 as a factor on the top. We also have that negative 1, don't forget about it. And we have a 1 plus sine x quantity squared on the bottom. I mean, you know 1 plus sine x and sine x plus 1 are the same thing. So one of those 1 plus sine x's cancel, and you're left with negative 1 over 1 plus sine x. So any questions with B? This is the derivative. I really should be writing dy dx here, but you don't have to. So now what I would like to do is talk about the chain rule. And you flipped the page already, and that's fine. We'll get to that in a second. But the only, is this true? I think so. The only exposure to the chain rule you have is when you differentiate something like that. This is the only exposure to the chain rule you have. And the derivative of this will be equal to 12 times 4x squared plus 2x plus 3 to the 11. And I want to attempt to explain the chain rule to you again. When I first explained it to you, I talked about, I believe, Xavier and Umberto and somebody else, and one person runs so many times faster than the other one. Remember that? Okay. What I have written down so far is not the derivative of the function with respect to x. What I have written is the derivative of the function, I'll say y, with respect to u. You know, if I said we have u to the 12, and you bring that 12 in front and you drop 1 from the exponent to get 11, and you write down 12u to the 11, you've found du dx, really, or dy du, rather. You've differentiated with respect to u. But the chain rule says you multiply by 8x plus 2, and this is the derivative of this u thing with respect to x. Are you starting to remember the chain rule? Okay. It is more global than this. U is an argument of a power. U is the argument of this power. So when you use the power rule, the chain rule says you multiply by the derivative with respect to x of the argument. Well, that's why this statement is true. The derivative of the sine of something that is bigger than x is the derivative of that thing, which will be cosine of that thing, multiplied by the derivative of the argument. So when we say, oh, times the derivative of what's inside is u. And I want to go back and show you something. When we take a look at A, this is sine of 2x, isn't it? Without differentiating, that's what that is. So what's the derivative of this function? I'll put brackets here just to make it clearer. The derivative of this function with respect to x is the derivative of this function with respect to 2x times the derivative with respect to x of 2x. That's what we had. I mean, without all this nonsense. I mean, I admit I'm just explaining stuff on the side, but the work involved here involved the product rule. Doing it this way, you're done. So that's what the chain rule amounts to, I suppose. And these are the formulas that I would give you on a formula sheet in high school calculus. All right, so determine each dy dx for each of the following. Sine of 3x squared. We know, and you will get to know more and more that this is the case, that this means that 3x squared is the argument of sine. If that squared was intended to be the squaring of the trig ratio, then you would see sine squared. So what is the derivative? Well, first and foremost, everybody, first and foremost, that expression is a sine of a thing, which means dy dx will be the cosine of that same thing multiplied by the derivative of that thing. And we're done, other than the fact that we like to write coefficients. Whether the coefficient is a variable or a constant coefficient, 6x can be thought of as a coefficient. We like to write it in front. We're okay with that? Let me throw a different question your way. What if I had y equals sine squared of 3x? Heck, you know what? Now that we're just making up questions, what's the derivative of sine squared of x? We're going to encounter this in a bit anyway, but I want us to think about this. What is the derivative of sine squared of x? Anybody want to stick their neck out? Jay? No? It's not cos squared of x. It's 2 sine x cos x. Because sine squared of x is a power. Sine squared of x is this. So first and foremost, this is a power. You wrap that 2 around the base, which stays the same, and you drop 1 from the exponent. Then you multiply by the derivative of the argument of the power. In other words, you multiply by the derivative of the base, or you multiply by the derivative of what you wrap the exponent around. Over here, we're multiplying by the derivative of what we were, I want to back up. Here on the right, we're going to multiply by the derivative of what we were powering. Do you get my drift, even though that's not really proper terminology? Here, we multiplied by the derivative of what we were signing. It's the argument that gets differentiated in the chain rule. So the derivative of sine squared of x is 2 sine x cos x, or sine 2x, by use of an identity. All right, let's try another one. X squared cos squared, x squared times cos squared of 3x minus sine squared of 3x. So this calls for the product rule, where the first is x squared, so we get 2x times the second plus the first, and now I have to multiply by the derivative of the second, which is a difference. So what is the derivative? So what is the derivative of cos squared of 3x? Well, this is what cos squared of 3x means. So this is a power of cos of 3x, which means if you differentiate it, you wrap the 2 around the base of the power, drop 1 from the exponent, and then multiply by the derivative of the base of the power. The base of the power was cosine of 3x. The derivative of the cosine of a thing is the negative sine of the thing. So when I, just to put the brakes on for a second, when I say with the power rule, and the base remains the same, that's equivalent to what I just did here when I say the derivative of cosine of a thing is the negative sine of the same thing. I don't want to differentiate that 3x yet. But the derivative of the cosine of a thing is not merely the negative sine of the thing, it's the negative sine of the thing times the derivative of the thing, times 3. So that is the derivative of cos squared of 3x. Minus the derivative of sine squared of 3x is 2 times sine of 3x raised to the 1 times the derivative of sine of 3x, which is cos of 3x, times the derivative of 3x, which is 3. So I'm going to clean this up a little bit. dy dx equals 2x cos squared of x minus, cos squared of 3x minus sine squared of 3x plus x squared. I just want to get it all on one line and clean it up a little bit. What do we have here? We have negative 6 sine 3x cos 3x and negative 6 sine 3x cos 3x. Yes? So that gives us negative 12 sine 3x cos 3x. Can we factor anything out? There's got to be something. Yeah. Yeah, that's it, right? Not much else. Not anything else. So dy dx equals x, and then here we're going to have 2 cos squared 3x minus sine squared 3x. And we took an x out. I'm going to do this. We took an x out, so we still have an x here. I'm going to take out, we'll just take out the x. We'll just leave it as this for now. Negative 12 sine of 3x cos of 3x. My 3 over here is a little wayward. It looks like a cube that should be 3, right? Any ideas where we can go from here? Any ideas where we can go from here? Any ideas, and I do this every semester, every year, what we could have done differently? Because we appear to be digging ourselves into quite a big hole here. Take a look at the original equation or expression. And we've run into this a couple of times. Declan?
You can simplify one of the brackets into cos 6x.
Yes. What we have run into before, and I can't remember which one it was, but we were differentiating something and we ended up getting in the numerator with the quotient rule, this was a month ago, a degree 5 or 6 polynomial that we had to factor, and it was virtually impossible to do. And the lesson we learned was you simplify first. So can we rewrite cos squared 3x minus sine squared 3x in simpler forms to begin with? Yeah. It's cosine of 6x with the double angle identity for cos. And by the way, you can start to do the same thing here. And you can factor negative 6 out of this and end up putting in sine of 6x. It's possible to do that. But if you do it from the beginning, so we're going to end that one there and write x squared, y equals x squared, times cosine of 6x, look how easy this is going to be to differentiate. The derivative of the first times the second plus the first times, now what is the derivative of the second? It's a cosine whose derivative is negative sine of the same thing times the derivative of the thing. Which simplifies just ever so slightly. I can take an x out and get that. And if you look carefully at our final line, look at this, 2 lines, and we're done. If you look at our final line here, this is 2 times cos of 6x, and this is negative 6 times x times 2 sine 3x cos 3x, and that's your sine of 6x. That's your double angle identity for sine. I think you would much rather do that. Always see if you can simplify first. Y equals tan of x squared. Uh-oh. We don't know what the derivative of tangent is, so what you need to do is think of this as sine of x squared over cosine of x squared. I like putting the brackets there, even though it's not often typed out that way. And then we can use the quotient rule. It's a curiosity thing. How many of you look at sine of x squared and say the derivative will be that? Okay, not yet. I wanted to find out if you're there yet. The derivative of sine of x squared is cosine of x squared, but the chain rule says we need to multiply by the derivative of the argument to get that. Isn't that what I wrote earlier? Did I write 2x? Okay. I just wanted to make sure. Times the denominator, which is cos of x squared. So derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. The derivative of cosine is negative sine of the thing times the derivative of the thing over the denominator squared. And I just want to run through that again. Derivative of the numerator is cos of x squared times 2x times the denominator, which is cos of x squared, minus the numerator, which is sine of x squared, times the derivative of the denominator, which is negative sine of x squared, times 2x over the denominator squared. So we can definitely do some factoring here. We can take out a 2x and have left cos squared of x squared plus sine squared of x squared. But cos squared of any angle plus sine squared of the same angle is always 1. So we end up with just 2x in the numerator over cosine squared of x squared in the denominator. Or, because we can, 2x secant squared of x squared, because the reciprocal of cosine is secant. Okay. Final example, I believe, cos squared of x over sine of x. I would like everybody to begin by writing down on the top what the derivative of the top is. Think about what cos squared of x means. Hope that what you ended up writing here is 2 cos x times negative sine x. And that set of brackets around the negative sine x is absolutely crucial. You don't want to write down something that looks like 2 cos x minus sine x, times the bottom, which is sine of x, minus the numerator, which is cos squared of x. And believe me, you're going to make that mistake. I mean, if you want to, I suppose you could do that. You could go, I just don't know why you would do it. Cos x, you'd be left with negative 2 sine squared x minus cos squared x. So what? I don't know what it would give you. If you want to start playing that game, then next thing you know, you're going to put 1 minus sine squared in for cos squared and tidy it up. I suppose you could do that. Maybe you would do that if you were finding critical values of x. Right? Because then you could change this to 1 minus sine squared of x, and you'd have a way to find out the critical values. But I think when you're just finding derivatives, this is good. When we get into deeper explorations with trig derivatives, we can start talking about that. I don't want to go there today. So you got to try to keep it straight. I know that it's right in front of you, but I also know that a good student is not going to be continually looking at it to find out what the derivative of sine of x is. So you have to have it in your head, and you just want to be careful not to make a mistake like I made there. So some problems dealing with this on page 313. There's a whole whack of problems. And Josh, you can go start your exam if you like. And get to work, and I'll come around and I'll help you out.
Could you put the textbook questions up on the board?
Absolutely.